Hi everyone, thanks for watching our demo. We're Team 1 and I'm Siming, and in this video we'll show how we turn our image to GPS model into an interactive product that a visitor can actually use on campus. So the core idea is simple. If you take a photo of Penn campus, upload it to our website, and the system tells you where you are and what you're looking at. So behind the scenes, we combine our Swin Transformer based image to GPS model, a small database, and GPT to turn raw images into meaningful location descriptions and show me tours of Penn. So quick recap. So from our model to product, in this class project, we first focused on machine learning side, like we collect images on campus in up to 8 directions per location. And we extract GPS coordinates from EXIF and split everything to train validation test set and train a Swin Transformer to progress latitude and longitude. That's what we describe in the core components of our report. For extra credit, we asked, what if this model wasn't just number in a notebook, but a tool the tourists can actually use? So I built this web app. So here's a live demo, like using the app as a visitor. Imagine that I'm a visitor at Penn, walking around at Penn Engineering grad. I see an interesting building, but I don't know what it is or any background history. So I open our site on my phone or laptop. Here's the interface, like on the left side, I can upload a photo I just took on the campus. And on the right side, the app will show the predict location on the map and text description, right? And just simple, like I upload sample photo from our data set. Once the image is uploaded, the front end send it to our backend API, and the backend runs to Swin Transformer image to GPS model to predict the latitude and the longitude. You can see here, the map zoom the predicted location and we place a marker near the corresponding building. For example, in this case, the model predicts that the photo was taken nearby Meyerson Hall and on the Penn campus. And predicting like GPS is nice, but coordinates alone are not very friendly to a tourist. So the next step is to call GPT. Like after we get the model predict latitude and longitude plus the image, we send a prompt to GPT that looks roughly like, oh, given this photo was taken near this longitude and latitude on the UPenn campus, please identify the likely building or street and write a short, friendly description or its background and history. So the GPT returns like this, like the name of the location, a short paragraph about the building or area. Here you can see the result like this. Like the model recognized like the design school, like this, and this is Meyerson Hall, and it also returns the location note and also a quick fact about latitude and longitude and our model, right? So now briefly explain how the systems is put together. Our app has 3 main pieces: the front-end web app built with modern web framework React and handles files upload the map and display GPT's answer. And our backend API receives the uploaded image from the front-end and runs our Swin Transformer model to predict the GPS coordinates and store the query and predict into small database so we can later analyze errors or usage patterns. And call the GPT API finally with a careful design prompt that includes the predict GPS location and sometimes a short textual description or context. So why is this useful? This setup is especially helpful like the tourists or new students who don't know the campus well. Like tourists or new students want to explore the Penn Engineering buildings and want quick background or what each building's for. Anyone who takes a photo and simply like, where am I and what's the interesting about this place? Because our model was specifically trained on Penn campus images and the prediction are more focused than generic global model. and GPT adds layer explanations that make the raw prediction much more informative. So that's it. Thank you for watching our demo.
Hi, this is Ila. I'll walk you through the core modeling pipeline. Firstly, let's look at how we handle the dataset split. As mentioned in the report, random splitting causes data leakage. To solve this, look at the block. Firstly, we stack all latitude and longitude coordinates into a NumPy array. Then, instead of random splitting, we use k-means clusters here. We calculate n clusters based on a heuristic of about 8 images per location. These fit predict functions groups images that are physically close to each other into the same location ID. Finally, we pass these location groups into group shuffle split. This is a crucial step because it ensures that if a location ID is selected for validation, all images from the location are removed from the training set, guaranteeing strictly zero overlap. Next, let's look at the data augmentation pipeline. Since our dataset is small, we needed to expand it without destroying the semantic features. We implemented this transforms composed block. For geometric changes, we used random rotation, specifically limited it to 15 degrees. We found in our ablation study that extreme rotations confuse the model about the horizon line. For photometric changes, look at the color jitter. We set the probability to 0.5 and the jitter factor to 0.4. Here's the code. This was a careful choice. We need a model to handle different lighting, but we must preserve the color distribution so it can distinguish, for example, red bricks from green stones. We also added random erasing at the end, which randomly masks small patches. This forces the model to learn global context rather than relying on a single visual cue. Moving on to the model architecture, we are using the Swin Transformer base from torch vision. We set stochastic depth probability to 0.2 right here in the constructor, which randomly drops layers during training to prevent deep network overfitting. Another important modification is here, the model head. The default Swin model comes with a 1000 class classification head. We replaced it with this sequential block. It projects the 1022-dimensional feature vector down to just two outputs, the latitude and the longitude. Notice we also insert a drop-out layer before the linear projection. This acts as a final regulator to ensure the regression head doesn't memorize the training data. Finally, I want to highlight our layer-wise learning rate decay implementation, which was key to our leaderboard performance. Fine-tuning a large transformer on a small data set is tricky because a high learning rate destroys pre-trained features, while a low one makes the head converge too slowly. We solved this by defining these custom param groups passed to the item W optimizer. In group 1, we use a least comprehension to select all parameters where the name does not include head. These are the backbone weights. We assign them a very conservative learning rate. In group 2, we select parameters that do contain head. For this, we use a higher learning rate. This implementation successfully decouples the learning dynamics, keeping the backbone stable and allowing the head to adapt fast to the GPS regression test. That covers all the core components in the model. Thanks for watching.